We begin today with a poem written by our hero. I'll read a single stanza. 43 quintillion plus problems Rubik posed for us. Numbers of this awesome kind boggle even Sagan's mind. Some chaps pry their cubes apart, in with calm intelligence, then reassemble to the start, not cricket, a rude game's afoot, and up with which we will not put. And true to form, the poem is complete with references. Any guesses? How about this? He's famed not only for building a juggling robot, but an electromechanical mouse that learned its way through a maze. I want to belabor a point here. The mouse was electromechanical, not electronic. It had no RAM, no integrated circuits. It merely used mechanical parts, circuitry, and magnets to exhibit a degree of artificial intelligence. Juggling, mechanical mouse, optimization of Rubik's Cube solving algorithms, to say nothing of his poetry of the same? Still not there? Here's the final clue. This genius, whose 1937 master's thesis, not PhD dissertation, his master's thesis, was described as possibly the most important and also most noted master's thesis of the century, invented and named the concept of the bit. Our man of the hour is the venerated Claude Shannon. I'm Josh Young, and this is Playing Odd, a podcast about complexity and information in the natural world. Episode 4, Information. Our quest from Episode 1 has been to understand the nature of information required to construct a brain. And yet, it has taken us to Episode 4 to get around to defining what we mean by information. For most of us, the idea of information, the definition, is self-evident. Information is something that tells us something that we did not previously know. The temperature outside at this very moment represents information that we don't immediately have, but can gain by looking at a thermometer or turning on a news radio station. Our ideas about information are not dissimilar to Renaissance ideas of matter. Anchored in Aristotelian thought, the idea was that matter originated as a raw material, a generic substance. This substance, through maturation or by external means, could be transmogrified into a more specific material, into a more derived material with specific characteristics. Gold, grass, cow. The revolution in thought that led us to our modern ideas was the concept of quantization of matter into atoms, what we refer to as elements. The nature of information was similarly amorphous until it too was quantized. The idea of an element of information, a base unit, was the invention of Claude Shannon. He defined this base unit as a binary digit, an element whose value could be 0 or 1. All other information could be built from this binary digit, from which he coined the portmanteau term bit. Combinations of bits allowed for more than 2 permutations, and 8 bits were sufficient to represent upper and lowercase characters and punctuation of the Latin alphabet. Our term for a collection of 8 bits is, of course, a byte. When we compare our hard drive sizes, we speak about megabytes and gigabytes and terabytes. Interestingly, and undoubtedly cynically, when we compare broadband speeds, they're generally given in bits to make them seem larger. The creation of the bit, the unit of information, allowed mathematical comparison of different sorts of information. Is a picture really worth 1,000 words? 1,000 words is roughly 5,200 bytes, or 42,000 bits. Although it is possible to produce an image that's only 5K, it would be an awfully small or awfully low-resolution image. So a picture is indeed worth 1,000 words, but any decent picture is worth a great deal more. This sort of information comparison would have been impossible without the idea of a unit of information. The amount of information in a string of letters is not directly dependent on the number of letters in the string. This sounds counterintuitive, but will become obvious with an example. The sentence I just spoke, this sounds counterintuitive but will become obvious with an example, comprises 70 characters including spaces. One might think that any sentence with 70 characters would require the same number of bits, that is to say, would contain the same amount of information. But what if those 70 characters were all the letter A, just 70 A's in a row? I could describe that sentence as 70 A's, but the phrase 70 A's itself contains only 5 characters. Therefore, the information contained in a string of 70 A's is no more than 5 bytes compared to the 70 bytes of the original sentence. As you might have guessed, a string of 70 A's conveys a great deal less information than a sentence might. And now we have the tools to directly compare the two. What is it about 70 A's that makes it so much more information sparse? The most obvious reason, and indeed the correct one, is that all of the elements of the sentence are the same. In more general terms, there is more similarity between elements in the 70A sentence than there are in the original sentence. Similarity within a dataset represents a decrease in the information conveyed by those data. At the end of episode 3, we had constructed a snowflake of infinite intricacy through iteration of a simple algorithm, substituting the middle third of each line with 2 additional segments forming a point. We asked whether this sort of iterative fractal process was sufficient to generate a structure as complicated as the brain, because if it were so, then this sort of iterative genetic expression would be our answer to overcoming the limited size of the genome in brain construction. Let's take the perspective that Shannon might have in evaluating the information that is added through the iteration to produce what we all can agree is an incredibly intricate snowflake. The answer lies in our comparison of elements of the snowflake, analogous to our comparison of characters in my sentence and in the sentence composed of a string of only A's. We found that 70 A's contained very little information in comparison to a sentence of 70 characters because of the similarity between elements, that is to say, letters in the string of 70 A's. Similarly, the snowflake demonstrates tremendous similarity in the outline of its shape. Indeed, self-similarity across scale is the defining characteristic of fractal shapes. Would it therefore be possible to compress our description of the entire snowflake into a very small data set with multiple repetitions? The snowflake, although infinitely complex and with limitless angles and points, contains very little information indeed. On reflection, this should come as no surprise. The generation of the snowflake required one simple rule repeated an infinite number of times. The shape, therefore, distills down to this simple rule. This is highly relevant to our question of a project of producing a human brain from a limited instruction set. We can see very clearly the distinction between intricacy and information density. The organization of veins in a leaf or branches of a tree, of bronchioles in the lung, and of venules in the retina, although intricate, contained much less information than one might otherwise expect. This would not be a problem for us if the brain were simply composed of identical branches of neurons, but it is not. The differences in connections between neurons is precisely what determines brain function, and the fact that they are not all the same is evidence that the amount of information required to build a brain is far more than iterative fractal processes can provide. This is not to say that fractal processes will not play a role in our eventual construction of the brain, but it is to observe that the iterative process will not add much information to the final product. Let me give you another analogy. We can describe the construction of a wall by beginning with a line of bricks with appropriately placed mortar. Our instruction to be iterated is to lay the next row of bricks so that their ends overlap with the ends of the bricks below. If we repeat this instruction, we can build a wall of any arbitrary size. We could build a wall much larger than any house that exists today, but we could not build a house. And this is because the structure of a house requires more information than this simple repeated instruction. it is important for us not to confuse arbitrary size and intricacy with complexity. Noise, both as a confounding and constructive element, will appear many times in these podcast episodes. Claude Shannon's information theory has a great deal to say about noise, much of it counterintuitive. Let's return to our exploration of the meaning of information. How much information is contained in the number 185.72? We now have the tools to answer this question. Since the measure of information is bits, we can ask, how many bits does it take to represent 185.72? Information theory answers this question by asking a question of its own. How many possible values are there? Let's say 185.72 is the stock price of an IBM share. In fact, let's say that 1.872 is yesterday's closing stock price. Did you know that? Let's say that you did not. Then the number 185.72 would indeed convey some information to you. However, it is easy enough to find out what yesterday's IBM's closing stock price was. And let's say that you already knew that it was 185.72. Then how much information is conveyed by my giving you yesterday's closing IBM stock price? The answer is none at all. You have no more information than you did before I told you something you already knew. But what if 185.72 is tomorrow's closing stock price? That would seem to convey a great deal of information, and indeed it does. Information theory would ask, as it did in the last example, how many possible values are there? Now, there are not infinite stock prices that the IBM share can have, but there are certainly many. Let's say in practical circumstances, there are 10,000 different values. To determine the correct answer amongst those 10,000 is to convey a great deal of information. To oversimplify things, the amount of information might represent 10,000 bytes. In actual practice, the calculations are done differently and distributions are taken into account, but even disregarding this, it is obvious, both mathematically and intuitively, that tomorrow's stock price carries a great deal more information than yesterday's stock price. Let's try something a bit less intuitive. Claude Shannon died in 2001. Let's say we are curious in learning the year of Claude Shannon's birth. We can safely say that the year of his birth must have been sometime between 1878 and 2000, since the oldest recorded human being lived less than 123 years, and it is unlikely that Shannon worked all of his marvels as a one-year-old infant. In the event, Claude Shannon was born in 1916. How much information is contained in the four digits 1916? If the number 1916 refers to the year of Claude Shannon's birth, then indeed some information is conveyed, since there were about 120 potential answers from which to choose. In order to determine the amount of information conveyed, we must necessarily ask, from how many possible answers does this data point come? Let's say the question is to choose a whole number between 1915 and 1916 inclusive. In this case, the number 1916 conveys only a single bit of information, since only two possible answers, 1915 and 1916, exist. Here's the counterintuitive part. Let's say that the question is not in what year Claude Shannon was born, but in what year Claude Shannon was born, followed by two random digits. For example, if the two random digits are 3 and 7, the answer would be 1916-37. If the random digits were 5, 6, then the answer would be 1916-56. By appending these two random digits to the end of Claude Shannon's birth, have we added information? We can determine the amount of information conveyed by the number of possible answers to the question asked. By adding two random digits at the end of the year of birth, we have multiplied the possible number of answers by 100. Does this mean that this number carries 100 times as much information simply by appending random digits? The answer, counterintuitively, is yes. There are more potential answers, and therefore there's more information carried by the actual answer. Let's explore this a bit. From where does this extra information come? Does it come from randomness itself? The answer is yes. How often do questions like this arise? Also, counterintuitively, all the time. Let's say that I want to transmit the number 1916 through a telephone line. After all, Claude Shannon did work for Bell Labs. Although 1916 is all that I want to transmit, there will be some noise in the transmission line because there's always some noise in the transmission line. Since my data are conveyed down this line as electrical signals, and since noise represents additional random electrical signals, the situation is entirely analogous to adding random digits to the end of the data I wish to transmit. This random data represents information. It is not the information I intend for the recipient to receive, but it is information nonetheless. Indeed, the reason it is so difficult to remove noise from signal is not because noise represents no information, but precisely because it represents information that is in addition to the information I am trying to transmit. In the example of the sentence and the string of A's, we observed that information density of a message is related to the similarity of elements within that message. Because each of the letter A's in this string of A's is identical to the next, it is possible for us to describe the string of characters more compactly than we could an actual sentence. Compactness, as you already know, is one of the main motifs of this podcast, since what we intend to do is to so compactify the connectome of the brain as to fit it into the genome if that's at all possible. Producing compactness is what we call compression, and we have already seen compression arise as a subject of several of these podcast episodes. We can use compression as a measure of the amount of information contained in a message. You can try this little experiment yourself. Copy a section of text of 1,000 characters. Save that file as sentences in a text file. Now create a second text file composed of 1,000 letter A's. Save this as A's in a text file. Now zip, sometimes called compress, each of these files. Which one of the files compresses to a greater degree? You'll see that the file consisting of letter A's compresses to a much smaller size. This is indicative of low information content. Now let's do the same thing with a file consisting entirely of random numbers, that is to say, noise. Obtaining random numbers is surprisingly difficult. When we use Excel or other software to generate random numbers or to use a random function, the numbers are not truly random but are generated by an algorithm to produce numbers that are random-ish. We refer to these as pseudo-random number generators, and for most scientific purposes, these are adequate. But for our exploration of information, they are not. Obtaining true random numbers usually means performing an actual physical measurement on something that is random. The classic example is the noise of the cosmic background radiation, the leftover radiation produced by the Big Bang. These numbers are felt to be genuinely random and are downloadable. In fact, there are websites that offer truly random numbers, and I've left a link to one of these in the show notes. If we copy 1,000 characters from a truly random data set and try to compress or zip the file, we will see that not much compression can be obtained. That is to say, noise, true random content, is almost incompressible, and that it is so information dense that there is no way to accurately summarize it. This is real physical evidence for us that noise represents maximal information density. To make this more palatable, we should draw a distinction between information that we want and information that we don't want. In electronics, information that we want is referred to as signal, and information that we don't want is referred to as noise. But as we have seen, noise actually carries more information than signal. And what we are really trying to do when we attempt to isolate signal from noise is to isolate a small information set from a larger information set. Information content of noise plays a significant role in cryptography, the science of encoding information so that it may not be observed by non-authorized parties. The most secure sort of information and coding is what we call a one-time pad. To try a simplified version of one-time pad encoding, all you need is a message that you wish to encode and a book. Take the message you wish to encode and look at the first character. Now, look at the first character of a book and add the two where A equals 1 and E equals 5, etc. up through Z equals 26. Translate this back into a letter and write that down as your encrypted letter. Continue this for your entire message, and you will have produced a code that is unbreakable unless the reader also has a copy of the precise book that you used when you were encoding your message. To make things more secure, you do not want to reuse any page of the book, hence the name, a one-time pad. This sounds immeasurably secure, except that it has one fault, which is that the book itself is not random, and it is possible to determine patterns of speech within a book that one can use to decode the message. To obtain a truly effective one-time pad, the book should be composed of truly random numbers. Intelligence organizations generate these truly random numbers through physical measurement of inherently random physical processes, such as radioactive decay and actual electronic signal noise. The randomness of this noise so completely overwhelms the information content of the message as to make it essentially undecipherable. This randomness, this statistical lack of any pattern within a data set, is referred to as Shannon entropy and is analogous to the mechanical entropy of physical systems. The revelation is that systems with greater entropy contain more information. In this episode, we learned about the quantum of information, the bit. We saw that information content of a message is related to the number of possible messages and also to the similarity of elements of the message to each other. We observed that highly intricate structures produced by repetition of a simple rule contain little information, and that noise, counterintuitively, represents great information density. We learned to compare information between datasets not only by their size, but by their compressibility. We can now revisit the genome with our new tools and see if we can fit an entire brain into 46 strands of DNA. I want to thank you, kind listener, for taking this journey through complexity with me. A bibliography for this episode, along with links to additional material, can be found at playingodd.com. I hope that this program will serve as an opening to a broader conversation. Please write to me with your questions or comments at josh@playingodd.com. Looking forward to spending time with you next week. I'm Josh Young.